Welcome to G Fun Facts Online, the show where we dive deep into the science and technology that's shaping our future. Today, I want you to do something simple. Just look around you. Look at the room you're in, the screen you're looking at, the world outside your window. Your brain is performing an incredible, effortless miracle. It's taking in a flood of photons and turning it into a rich, three-dimensional, meaningful experience. For decades, we've been trying to teach computers to do the same thing, to see the world as we do. We've had some incredible successes, but we've always known there's a fundamental piece missing, a gap between how our machines see and how we, as humans, perceive reality. But what if I told you that is about to change? A new frontier in artificial intelligence is opening up. One that takes its inspiration not just from the idea of a brain, but from its very architecture, its physical layout. Researchers are building a new class of AI that doesn't just mimic the function of our vision, but its form. It's a breakthrough called All-Topographic Neural Networks, or ATNNs. And it's not just set to revolutionize AI, it could unlock the deepest secrets of how our own minds work. So how did we get here? And where is this incredible new technology about to take us? Let's find out. To understand why ATNNs are such a big deal, we first need to talk about the reigning champion of computer vision, the Convolutional Neural Network, or CNN. If you've used social media that automatically tags your friends in photos, or if you've seen footage of a self-driving car navigating a busy street, you've seen a CNN in action. For years, these networks have been the absolute workhorses of AI vision. They are designed, in a very broad sense, to emulate parts of our own biological neural networks. Think of a CNN as a detective with a very specific set of magnifying glasses. One magnifying glass is trained to spot vertical lines. Another is trained to spot horizontal lines. Another to find curves. Another for a certain color or texture. The convolutional part of its name means that the network takes each of these magnifying glasses and systematically slides it across the entire image, from left to right, top to bottom. It's looking for its specific feature everywhere. If it learns what an eye looks like in the top left corner of a picture, it can use that exact same knowledge to find an eye in the bottom right corner. It's a copy and paste approach, and it's incredibly powerful and efficient. It's the reason AI has gotten so good at recognizing objects in photos, no matter where they are in the frame. But here's the catch. The human brain doesn't work that way at all. Our visual system isn't a copy and paste machine. Think about your field of view right now. The light hitting your retina is projected onto a part of your brain called the visual cortex. But it's not just a jumble of data, it's a map. It's what neuroscientists call retinotopically organized. This means that there's a literal spatial map of the visual world preserved in your brain tissue. Neurons that are next to each other in your visual cortex are processing information from points that are next to each other in the real world. The top of your visual field is processed in one area of the cortex, the bottom in another. The center of your vision gets a huge amount of brain real estate, while the periphery gets less. It's not a one-size-fits-all system. It's specialized. Different parts of your cortical map are dedicated to processing specific locations in your field of view. This topographic organization is a fundamental, cornerstone feature of how primates see the world, and for the longest time it's been missing from our mainstream AI models. This is the gap that researchers at Osnabrück University and Freie Universität Berlin decided to bridge. They asked a brilliant question. What if we built an AI, not just to recognize what's in an image, but to do so with a structure that mirrors the brain's own visual map? And from that question, the All-Topographic Neural Network was born. As the name suggests, ATNNs are designed from the ground up to maintain that topographic map-like organization. Instead of having feature detectors that are copied and pasted across an image, an ATNN has what they call a cortical sheet. You can picture this as a two-dimensional grid within the AI, a virtual piece of brain tissue. On this sheet, the AI's virtual neurons are spatially organized. Neurons that are neighbors on the sheet are tuned to detect similar features, like a specific orientation or color. As you move across this sheet, the features that the neurons are looking for change smoothly and gradually. It's a far more organic and far more biologically realistic model of how we see. This is achieved through a clever addition to the AI's training process. They introduced a new rule, a new piece of code they call a topoloss function. You can think of it as a kind of coach for the AI. During its training, where it looks at millions of images, this topoloss function gives the AI a reward every time it organizes its internal neurons into a smooth, brain-like map. It's a brain-inspired bias that encourages the network to develop this topographic structure naturally, rather than having it rigidly programmed in. So instead of just asking the AI, "Is this a cat?" we're also asking it, "Can you organize yourself in a way that makes sense, in a way that reflects the structure of the world you're looking at?" This marks a profound shift in thinking. We're moving from building AIs that are simply powerful problem solvers to building AIs that are more aligned with biological reality. The goal is no longer just to match the brain's performance, but to understand and replicate its principles. So why go to all this trouble? If CNNs work so well, why do we need a new, more complicated model? The answer is that the benefits of this brain-inspired approach are immense, and they go far beyond just getting slightly better scores on an image recognition test. First, and perhaps most obviously, is the improved biological realism. For neuroscientists and psychologists, ATNNs are like a dream come true. For the first time, we have a computational model that doesn't just see, but sees in a way that is structurally analogous to us. Researchers can use these models as a kind of digital laboratory for the brain. They can tweak the model, damage a virtual part of its cortical sheet, and observe how its perception changes. This could give us unprecedented insights into real-life visual disorders or the effects of brain injuries, helping us understand the very neural underpinnings of our perception. Second, this structure could lead to enhanced accuracy and efficiency. The brain's map-like organization wasn't an accident. It was honed by millions of years of evolution. It's incredibly good at what it does. By mimicking this principle, ATNNs might unlock new levels of performance. The real world has spatial rules. The sky is up. The ground is down. Objects have a predictable relationship to each other. A topographic system, which inherently understands spatial relationships, might be far better at navigating the complexities of a real-world scene than a system that treats every part of an image as an isolated puzzle piece. Third, and this is truly fascinating, ATNNs help us understand the why behind the quirks of our own vision. For example, it's a well-documented fact that humans have spatial biases. We're generally better at recognizing objects in the center of our vision, and we're slightly better at seeing things in our lower visual field than our upper. When researchers tested the ATNNs, they found the exact same biases emerged naturally, without being explicitly programmed. The models were simply better at seeing things in the same places we are. This provides a direct computational explanation for our own human experience. These biases aren't a flaw. They are a direct consequence of having a topographic map-like visual system. And finally, there's a huge potential benefit in energy efficiency. Our brains perform incredible computations using only about 20 watts of power, about the same as a dim light bulb. The massive data centers that train today's big AI models, by contrast, consume enormous amounts of energy. Early research suggests that the smooth, orderly topographic organization of an ATNN could have a metabolic benefit. A well-organized system is less chaotic, and it's plausible that it could operate on a much lower energy budget. As AI becomes more and more integrated into our lives, developing sustainable and scalable AI is not just a goal, it's a necessity. The potential applications for this technology could reshape entire industries. Think about autonomous vehicles. A self-driving car powered by ATNNs wouldn't just identify a pedestrian, a bicycle, and a traffic light as separate objects. Its internal map-like structure would give it a more holistic, intuitive understanding of the entire scene, and the spatial relationships within it. This could lead to a leap in safety and reliability, creating autonomous systems that perceive the world less like a sensor and more like an experienced driver. In medicine, these networks could revolutionize the analysis of medical images like MRIs or CT scans. A radiologist doesn't just look for pixels. They understand the anatomy, the expected layout of organs and tissues. An ATNN, with its inherent spatial organization, could assist doctors by analyzing these scans in a way that more closely mirrors a human expert's understanding of the body's topography, leading to faster, more accurate diagnoses. And of course, for neuroscience and psychology, ATNNs are a powerful new tool to place under the microscope. We can use them to test hypotheses about brain function that were previously untestable, potentially unlocking new treatments for visual disorders and gaining a deeper understanding of the very nature of consciousness and perception. The development of all-topographic neural networks represents a genuine paradigm shift. We are witnessing a move away from pure brute force engineering and toward a more elegant, biologically inspired approach to creating intelligence. By humbly looking at the blueprint that evolution has already perfected, the human brain, researchers are building AI that is not only more powerful and efficient, but also more understandable. An AI that is more like us. This research is still in its early days, but it holds the promise of a future where our technology can see and comprehend the world with a nuance and intuition that was once the exclusive domain of biological life. The long journey to create truly intelligent machines is far from over, but with innovations like ATNNs, we are taking a significant and fascinating step closer to that goal. And in the process of teaching our machines to see like us, we might just learn more about ourselves than we ever thought possible. Thank you for tuning in to G Fun Facts Online.